Okay, so we are going to finish up this homework here. We're looking at 7. 7. If the coefficient of sliding friction is 0.2, what work is done by friction? So, work is equal to force times distance. In this case, it's the force of friction kinetic times distance because it wants the work due to friction. What is the friction force? This is a horizontal force pushes a sled. There is no angle involved here. You do not have that sled on a string. And by the way, it ticks me off because when you buy a sled nowadays, they give you about as much string for you got to be bent over like this. So the first thing you need to do is go to the hardware store or something and buy a longer string, right? So you can make it easier on you. So this is just going to be the force of weight times, this is mu times the normal force times distance, right? Because the force of friction is mu times normal force. And since there's no angle, the normal force is equal to the force of weight. So the work done here is going to be mu mgd, isn't it? Mu mgd? It should just come out to be mu mgd. What else do we have on this?
I know, dude.
34, none. But you've got the right answer. It looks like this is plugger, huh? Yeah, you've got. I would say you've got this, though. There isn't anything tricky to this, right?
That's what I did, is took the numbers on our homework and just replaced what you had in there, and I came up with a number. Do I know if it's right or not? No.
So this is just going to be MGH, right?
734 is MGH.
Potential energy, 12 meters, release to fall. What is the potential energy, the kinetic energy at the highest point? Okay. So at the highest point here is 12. The potential energy is MGH. And at MGH, this is 18. The height is 12 meters. What do we get for potential? How much? 216.8 joules. So that's the potential energy on top. It's lifted. What's the kinetic energy up here? Kinetic energy equals 0. So the kinetic is 0, the potential is 216.8, and the total is 216.8, right? 3 meters above the ground. So it looks like they don't really show this, but this is allowed to fall. It has some velocity here, correct? So what's the total energy? The total is going to be 216.8 joules, right? You know it's 216.8. It has to equal what it had here, conservation of energy. The potential will be the easy one. MGH, where H is 3 this time. That's the easy one to plug in, right? What's your potential energy right here? Oh, I'm not saying that. I'm saying the total energy is 216.8. These two added together are going to have to be 216.8. So if we figure out MGH, which is the fastest and easiest, when you plug in the same mass of 18 times 9.8 times 3, what do we get for potential? How much? Can't be 529 if we only started with 216. So then this number here is wrong. Is it 9.8 into this one? The top one is 2116.8. Whoa, we're off to a rough start. 2116.8. So this is 2116.8. And when this is 3 meters here, this is 529.2. So if that's 529.2, together they got to be 2116. So if I minus 21.6.8, that kinetic here is 1587.6. And at the ground, the potential energy is 0, and the kinetic energy would be the total again, 2116.8 joules, right? What else do we have?
No, put back, I didn't get it all.
Whoop, 29.
Okay, now I'm gonna take you.
39, right? Not 29. 39? 29 or 39?
Somebody make up my mind.
29, all right.
We'll see what number he pulls up, but I can't see it.
All right.
I'm done.
29. Well, this is 0.8 meters, right? Relative to the floor. So if that's 0.8 meters, obviously floor, table, chair, MGH here is going to be
Talk it to me and I'm trying to write a picture of the
2, 9.8, and 0.8, right?
In C, why is the height -2.2?
Oh, wait a minute, no. What? Oh, okay, hold on. Find the potential energy of the book relative to the floor. Oh, wait. I screwed this up. Oh, this is the table. No, I didn't screw it up. This is the table. So this is right. For A, this is the correct answer for A. You're going to use the table, correct? For B, the seat of the chair. Now, for the chair, what is the potential? So it would come off the table and hit the chair. So what is the difference in height between the chair and the table is 0.4, right? So you'd plug in 0.4. Or yes, half of your first answer. For this is B, 2 times 9.8 times 0.4. In C, you're saying relative to the ceiling. So, and you're saying that they have a negative 2.2? Yeah, I think what they're saying then is if it starts on the table, and then, I don't, relative to the, oh, it does say, relative to the ceiling from the floor, why won't we just plug in 3 meters then?
Okay, I think B is the thing that confuses us because I think the answer for B when it falls off the chair to the ground is the same as the table to the chair. I'm pretty sure the A, B, and C are where it falls from.
Well, it,
Clock.
well, it doesn't, it's just saying if it's this is A, this is B, and it really doesn't even say it's falling. And then in C, you're just plugging in this number, and then this number, aren't you? But they have a negative for the last one?
They have -2.2 for their height.
Relative to the ceiling, 3 meters from the floor. Okay, that's right. That's right. It's not 3. Let's read this. It says the book is sitting on the table. But if it's sitting on the table, what is the distance between the table to the ceiling? That's where the this 2.2 is coming in. So,
It's negative 2.2, would that mean it has negative potential energy because it takes kinetic energy to get it out to the ceiling? Or is that not?
I don't know why do they have that negative in there.
It would make sense because it's lower than the ceiling, so to get it up to.
Because they're using like a -9. They're saying that you'd have to raise it up there against gravity. Gravity acts negative. They're probably asking that way. On the test and the quiz, when it has a goofy negative thing, I take those signs out. Is this? I'm not sure. I'd have to go back in the book and look at why they're calling this negative. Well, it depends on how you're putting in positive work to lift it, and it's gravity. Usually you put positive work in to lift it, and gravity's negative work bringing it back down.
That's the way I thought about it.
But you'd have to put in positive work to lift it. I would think that would be a positive answer, but.
We're not finding this negative, we're finding potential, so it's less potential, and it moves up here, so it's kinetic, take out the
How about 39? Anybody do 39? Okay, we're doing 39. The reason we're doing 39 is this. This is our next lab. This is the exact lab. This question right here. Star it, laminate it, color it, whatever you need to do. This is for sure, this is the lab.
I was hoping John had something to do with the balls.
You sound like the students setting it up. Get that glassware out. Pretty soon, I'll fill this with water and... The yellow liquid. What does it look like? Say exactly what you think it looks like. Yeah, it's fermented. It's whiskey. It's undistilled whiskey because it's corn mash from the ACE ethanol, and we added brewer's yeast to it. So it's fermented alcohol. Now, am I going to be able to do this? Probably not. Okay. So here's our launcher. Here's our launcher. Now, here's what we do. There is this, see this right here? If I set this to 0, this thing right here, if I set this to 0, this little peg thing here, when I launch it into that, it's going to get caught. It's going to go up. See, when this goes up, it moves that angle, doohickey, and it's going to come back down. So, now, when I hit this thing, if I reset this, and if I fire this,
Get off the spring.
oops, I know the maximum height because it just registered this angle, correct? And from there we can calculate this. That's the next lab. So I want to do this calculation here because it's part of the homework but sets us up for the lab. So let's look at this. Now, this is our ballistic pendulum. This is a 40-gram ball. Ours is approximately 65 grams, as you hopefully found out yesterday or the day before. 500 grams suspended mass. Okay, this is then the catcher. Now, by the way, this is how they used to do it in class. The instructor would pull out a .22 gun, and there would be a block of oak suspended from the ceiling right here in the classroom, and they'd shoot the darn thing with the gun.
I want to do that lab.
Right? And then, oh no, not a big block of oak. A big block of oak would go up into the air like this, and somehow they'd keep track of how far it went up, and you can calculate the velocity of that .22 shell. So actually they have that gun mounted in a stand, right? So they can't miss. And so here's what we've got. After impact, the two masses rise a vertical distance of 45 millimeters. So this H right here, after that thing is fired in and it's caught, here's our pinball. If I describe it as a pinball, it's kind of like, it's not the size of a pinball, but so this thing is going to come in. It looks like an Easter egg, yeah. It's going to get caught in the catcher. This rises 45 millimeters. How many meters? 45 millimeters. Yeah, 0.045 meters. Okay. Now, let's see if we can figure this out. After impact, the two masses rise a vertical of 45. Find the velocity of the combined masses just after impact. Combined masses. So the combined masses right here, there's two masses. This mass of the catcher empty. Maybe I should put it that way. And on top of these, weight. Somebody wrote the word weight. On top of these is already written this weight, 246.5 grams. I know it's upside down, but it's not weight, right? I don't know who wrote that, but somebody's already massed this whole thing on a scale. Or there's an effective mass of that catcher. So this catcher, MC, is 0.500 kilograms, right? The ball coming into this, the egg, is going to come in, and that mass of the ball was 0.040 kilograms. For our lab, it's going to be about 0.065. Now, when we do the lab, we're actually going to calculate the velocity of this ball again. And we're going to lose about 75% of our energy here, about 78%. But here's what we've got. Mostly friction, sound, all kinds of stuff. Heat, because it's gonna get a little warm when it catches it. What is my potential energy here on top? What is my potential energy here on top? At the maximum height, what's my kinetic energy on top? All right, my kinetic energy at the top is 0. My potential energy here is going to equal what? Catcher in the ball, yes. It's the mass of the catcher plus the mass of the ball, GH, right? Because they're together. What we're trying to calculate is what velocity down here is it heading up at? At the bottom, what's our potential energy? 0. Let me turn this light off. What's the potential? What's the kinetic energy down there? Yeah, my kinetic energy at the bottom is going to be 1/2 mass of the catcher plus mass of the ball. Velocity squared, isn't it? Now this velocity, let me clarify. This is the velocity of the ball and the catcher together. Let's put BC on that, right? Because when we do lab, we're going to add one more calculation to this. So the kinetic energy at the bottom has to equal the potential energy on top, right? And our masses are going to cancel out, aren't they? So in this case, if I come over here and just say the energy at the top equals energy at the bottom, right? The energy at the top is MC plus MB GH equals 1/2 MC plus MB velocity of the ball catcher together squared. Yep. Same thing. Square root 2GH again. Right? Because the mass cancels out. Now we're going to add what does the velocity of the ball come in here for lab. We need to use conservation of momentum, which is coming up. This is conservation of energy. We're going to lose 78% of our energy. So when we go back and calculate for lab, we already know what velocity that ball comes out of that projectile at. It's like 3.4, isn't it, meters per second? Most of you have calculated the velocity of that ball a couple times now. It's about 3.4. So when this thing hits at 3.4, we can calculate that kinetic energy. Then the kinetic energy of that ball all goes into raising this thing. We only get, like I said, we lose 78%. It only raises it about 22% of what you would figure if everything was, if all the energy went into it. Okay, so that's that baby. Anything else on this homework? 56, I can try. 56. The answer key's wrong on that one? Okay, 56. To what height can a 400-watt engine lift a 100 kilogram in 3 seconds? So, this is power, work divided by time. Work is force times distance divided by time. Okay. So, to what height can this 400 back? We better do a drawing here. What force is it lifting? Where's my drawing here? I don't know if I should hook. It's lifting this, correct? So if this is hooked to a motor, isn't my force it has to lift is mg? Okay. So, and it's going to lift it up vertically, so we can actually substitute this in. mg, it's going to lift it up in the y direction divided by time. Oh, crap. This force is mass times gravity, and the height is my y. So I'm going to solve this for y, and I'm going to get PT divided by mg should equal my y. The answer key's wrong? Okay. Make sure you're putting in, oh, that is kilograms already. Okay. The answer key says what? Okay. And what's the answer? All right. Anything else on this? All right. I'm going to fire up this air track, and I want to show you what we're going to do. Is this upside down? Yep. So I need to leave it like this then, and I need to flip it. There, it's not upside down. Let's see if we can get this air track to show up a little bit. Okay. Now, watch this. We're going to talk about momentum. What is momentum? Mass times velocity. Right? Momentum, mass times velocity. And here's what we're going to be talking about.
What's up, Richard?
If this is basically an air hockey thing, right? So that when I put this on here, first of all, I don't know if it's level. It's not. It's going this way, and we could level this by raising these legs, but I don't have time. Okay? And this is pretty frictionless, right? But now I'm going to collide that one, just like when you're on a pool table, with this one. So if I set this one in here, and if I allow it to collide with it, now if they have the same mass, this should be what should happen. Let me start this again. This one is at rest. Okay? If this is a pool ball that is at rest, and if you do this right, this one here is going to come in and hit it. That one goes out at the same speed that this one hit it with, if they have the same mass. The momentum is conserved and transferred. So that if I just set this going now, I wish they keep hitting each other, and they end up going the same mass that they're getting hit, or the same velocity, correct? If they have the same mass. And they have relatively the same mass. And this thing is really, yeah, a little bit, because it's really off. Because after they hit, that one stops. This one's going to hit it. This one should not be going that way, but it goes that way a little bit. But now, look what happens. Let's change the masses. So I'm going to add these masses. This one here has a lot more mass now. This one is going to have a lot more momentum. So if this one, moving at maybe 1 meter per second, hits this one, which is a lot lighter, it's going to kick that pig out fast, isn't it? And likewise, okay, so watch. This one's going to come in. If it hits this one, that goes a lot faster. And now, I'm just trying to... Plus you can run them the same way now. What if there's a collision going the same tube, this one slowly this way. I'm going to set this one up slowly this way, and I'm going to ram this one into it. What's going to happen? This one should get a little boost continuing the same direction. Okay, so I'm going to start that one that way. That one stopped. You can actually get that one to go the other direction. That one just bounced back the other way, right? So you can actually have the collision where, depending, this one coming in, that's going backwards, right, for a collision. So these are elastic collisions. But now we can change it by putting a needle in there into one. Let's go back to the same mass. needle and a wax plug in the other one. So now when they hit, they are going to be a combined mass. So now they're going to stick together. Velcro could do the same thing. But if these have the same mass, let's say this is 1 kilogram, 1 kilogram. This comes in at 2 meters per second. When they combine, what's going to be the speed of their combined mass? It's going to be half of what it comes in at. So if I just go like this, and they lock together, it should be going half. If they have the same mass. That one hit kind of hard, but... that is an inelastic collision. Now, momentum is conserved for all of our collisions, but in this one, kinetic energy is not. So we're going to talk about the conservation of momentum and the conservation of energy for these collisions. That is an inelastic collision. Okay, things coupled together for an inelastic collision. It goes into sound, heat, and... Now, let's look at least we got to get a momentum. So our example of that, I just wanted to get started a little bit, was this. Come on. The total linear momentum of colliding bodies before impact is equal to their total momentum after impact. So we had two masses on the air track. You'd have momentum 1, momentum 2. This is before impact. This is after impact. Okay? Momentum is just mass times velocity. These are not stuck together. These are... well, momentum is just mass times velocity, kinetic energy, 1/2 mv squared. Joules, energy. Momentum isn't quite the energy. So this is where we're going. We're going to talk about conservation of momentum, and then once we add conservation of energy to this, we can solve some more complex problems. We left off up here. We did this problem. We got 4 minutes is all. Let's do this Venus Williams one, though. What do we got here? French Open serve, that's 130 miles an hour. What is the average force exerted on a tennis ball? So we're doing impulse momentum. The force times the contact time is equal to our change in momentum. Now, P is always momentum, and momentum is always, if it changes, it's going to be mass times V final minus V initial. So let's see what we know here. Assuming the ball's speed just after impact is 58. Yes. Nope, this is not the same P, right? This is momentum P. This is little p. Big P is power. So V final out of this is 58 meters per second. It reaches a speed of 58 meters per second. Initially it's 0. The mass of our ball is 0.001 0.057 kilograms. The contact time, we're looking for force, 5 milliseconds. How many seconds in 5 milliseconds? .005 seconds. So that is your time, yes. It's down here, it's barely. Here's our 5. Can't see it by much. What's the average force? So the force would come out to be what? Divided by .005. 661? We get 661, don't we? All right. I will stop there. I'll get a take-home quiz out to you in the next hour, I think. Now, can we do, what do we got for homework? Do I have that printed out here? What can we do for homework on this? I do have it printed out. Oh, well, you don't have anything to study for. Let's see what you can get started with for homework here. For homework,
Our homework is to study for the test.
no, we don't even have that.
That's just until like the next.
Now be careful on this homework. If one of them's going right, or one of them's going opposite directions, one's going to have a positive velocity, one's going to have a negative. Just do 1 through 10 on this baby. On chapter 8. 1 through 10. On this chapter 8 homework. Okay, 1 through 10 on this homework.